So just so you know, most of the professors who are attending the first week, not all of them, will not be attending the second week. So we'll have a bunch of new professors in the second week. So I think some of them are leaving this week, and there will be like 12 professors arriving next week. Neutrino guys, mostly. So anyway, so you have Carlos Yaguna talking about Isospin-violating dark matter. Could you please, IT, there, set up the clock? Set up the clock, please. So you have about 35 minutes, okay, Carlos? Thanks.
Okay. So thanks a lot. I will be discussing about this idea of isospin-violating dark matter. So we will see what actually is meant by this phrase, but also why it has become relevant now during the last days or years. So I did some work on this idea, so you can find on these papers. So the problem we are trying to solve is to determine the nature of dark matter. Okay? And there are different labels which you can try to answer the question of what exactly is this nature. Right? For instance, a first idea would be to identify the kind of particle that we actually, that constitutes the dark matter. So is it really a WIMP, an action, or it is something different? Okay. This would be like the first step. Then, once this is kind of determined or clear, we can go to a second step and to try to determine what are the properties of these specific particles. Okay. So we can try to answer or find what are its mass, its spin, its quantum numbers. Okay. These properties would determine essentially, for example, how this particle interacts. Okay. And then, from this, we would try to reconstruct how this particle behaves, and essentially we would try to find what is the correct model for dark matter. Okay. So this is the end goal. This is what we want to find at the end. This is what we want to find at the end. But to get here, we have to go through a long process in which we first have to find signals of dark matter, analyze them, trying to reconstruct these parameters, and finally, from these parameters, trying to find what's this correct model for the physics that explains the dark matter. Okay. And it becomes more and more challenging as we move from here to here and here. Okay. So in principle, it's not that difficult to answer the first question once you have a signal. Okay. So for example, we know that there are detectors that are designed for WIMPs. Okay, so if you find a signal there, you know that it's certainly not an action. Okay, it is a WIMP. Then, but once you have signal, from this signal you have to reconstruct the properties. Okay, it's not so trivial, but you can try to do so and find some determine some quantity related to the dark matter particle, like the mass of the interaction cross sections. And then you need to find additional observables in order to finally try to find this correct model of dark matter. Okay, but that's the goal. That's the goal. So we will be working here during this talk, let's say, at this second step. Like, okay, what if you have a WIMP and then you want to determine some of its properties, given a signal, for instance. So we will focus on WIMPs. WIMPs are very special dark matter candidates, so they've been well studied and they have many interesting properties. So what is special about them is that they are produced in a very simple way, so you don't need assumptions, essentially, special assumptions in order to explain how this dark matter is produced. So it's just a thermal process, a freeze out, and we know that the freeze out is also the way, for the neutrinos, the neutrino background was produced. So it's just standard cosmology is something that is very natural. We also know that WIMPs appear in many different extensions of the standard model. So there are different models which in principle were not even designed to explain dark matter, and they contain WIMP particles as dark matter candidates. Okay? So most of the models that you find in the literature for dark matter are actually models for WIMPs. And another nice feature of WIMPs is that they are detectable. Okay? So with our technology today, we have the possibility of detecting these particles and finding a signal for these particles. Okay? So that means that we also can exclude some of these models. And that's how we make progress in science, right? We exclude more and more possibilities until we find what is left. So we will focus on these WIMPs. And WIMPs can be tested in different ways. So the three usual ways are indirect detection, collider detection, and direct detection. And they are illustrated here. So in indirect detection, what we look at is the annihilation products of the dark matter particles. So typically what you have is photons, neutrinos, and antimatter. In collider, what you have is the production of the creation of dark matter. In particular, on the LHC, dark matter can be produced from these proton-proton collisions and then observed via missing energy signals, essentially. They don't leave any other trace at colliders. So you can also produce these particles there and study its properties, for instance, at the LHC. And finally, we have direct detection, which is this plot in this direction. So now what we have is the scattering between a dark matter particle and a standard model. In this case, is a nucleus. And this produces a nuclear recoil, so that can be detected. So in this case, what we are observing is actually the dark matter particles that are here around us when they interact with matter. Okay, it's just that this experiment have to be very sensitive because this recoil is tiny. It's of the order of keVs. And we will focus here on direct detection, which is the most promising way to detect dark matter and to confirm that it is actually the dark matter that we are detecting. So here is an example of what direct detection experiments look like in principle. Okay. So this is a TPC, what is called a TPC. So here you have some materials, so xenon, let's say, or argon. And then this is your target. So the dark matter particles are around us. And these dark matter particles are moving around. And from time to time, one of these particles will interact with one of the nucleons in this material and will deposit some energy. Okay? And this energy gives rise to photons and to electrons. And this can be measured. And from that, determine that there was this kind of interaction. Okay. So these direct detection experiments, I mean, this is nowadays is a mature technology. Over the past years, we have obtained stronger and stronger limits, and there is a well-defined plan to get even better sensitivities over in the near future. Okay, so it's a promising way in which the dark matter could be detected soon. So what does the signal in these direct detection experiments depend on? Well, what they measure is the number of events and the energy of these events. So, and this quantity is the recoil spectrum, so it's given by this formula here. So you have, this is the local dark matter density, you have the mass of the dark matter particle, the mass of the nucleus. Then you have here some functions of the velocity. So this is the velocity of the dark matter particle, the velocity distribution of the dark matter particle. Then you have this differential cross-section here of the interaction that depends on the energy and the velocity. Okay. So here there are quantities that depend on the astrophysics, which are like, for example, the velocity and the velocity distribution. There are also some factors that depend on the fundamental properties of this dark matter, and mostly they are inside this quantity, this sigma dE. Okay. So this interaction depends or can be decomposed in two parts. One is what is called the spin-independent part and the spin-dependent part. So this is spin-independent, spin-dependent. So these quantities here are called nuclear form factors. They depend on the nuclei. And most of these experiments that are currently running are spin-independent experiments. Okay, so they are designed to be particularly sensitive to this kind of interactions. And this spin-independent cross-section is in turn written in this way. And here you can see that, remember, this is the spin-independent cross-section with the nucleus. Okay, so it essentially has two contributions. One coming from the interaction with the protons in the nucleus, and another one coming from the interaction with the neutrons in the nucleus. Okay, and this is a coherent interaction. So essentially, what you have is the sum of these two contributions squared. Okay. So from the particle physics point of view, these signals are direct detection experiments depend on just three parameters. These three parameters are this so-called FP, which is the coupling of the dark matter to the proton. Then Fn, the coupling of the dark matter to the neutron. And then is the mass. So the mass appears here and is also in this factor, the mass of the dark matter part. Okay. So this is all you need from the particle physics point of view in order to predict what the signal is. Okay. So you may have 10 different experiments, but the rates can be predicted in terms of just three parameters. Okay, no more than that. So this is one of the crucial observations. So you don't need more than three. Okay, the mass and the coupling of the dark matter to the proton and to the neutron. Now, at a fundamental level, these couplings will in turn depend on the model, okay? On how dark matter particles coupled, for example, to quarks. But for us, we will take them simply as free parameters that are to be deduced or extracted from the data. Okay? So once you have a signal, you want to be able to determine what FP and Fn are. Okay. So these are some of the direct detection limits that we have been obtained over the past few years. Here we have data from 2017, 2018, and 2019. So you see that this is a very active field of research indeed. There are several experiments. These are all international collaborations, and these are located in different places. So for instance, these are the most famous LUX, which is in the US, Panda X in China, and Xenon 1 ton in Italy. Then we also have DIP, which is in Canada. Dark side is also in Italy. Okay, super CDMS, but we won't discuss much about it. So you see, these bounds, so here from this view, you see that the most relevant bound is from Xenon last year, but we also have this recent bound from depth, which is from this year. Okay. Now, as you see, these limits are usually presented in this plane. Okay. So if you can present a limit in a plane, it means that it depends on just two parameters. Okay. But how come you can do this when we say that the signal actually depends on three parameters, not on two? Okay. something seems to be missing here. Okay? And indeed, when they present these figures, they are making extra assumptions. Okay? They are not considering the general case. And the extra assumption they are making is that the coupling to the proton is equal to the coupling of the neutron. Okay? So they are saying the dark matter interacts exactly in the same way with the proton and the neutron. Why? Why do they impose this condition from the very beginning? Well, there is actually no reason to impose it. I mean, I guess it's simply because it's easier to obtain a 2D plot than a 3D plot. But we don't know if dark matter actually behaves in that way. I mean, we haven't even detected the dark matter interaction, so obviously we don't know if it couples equally to the proton and the neutron. And from the theory point of view also, there is no reason to expect that the coupling of the dark matter particle is the same. But that's what they do in these plots. And it's a very strange situation because in general you expect these two couplings to be different. But it's been assumed for a long time that they are equal, and that's how the results are presented. So actually, when you consider that they are different, then it receives a special name. Okay? So we got it all wrong. So when we assume that Fp is different from Fn, we call this isospin-violating dark matter. It should be the other way around. When you assume that they are equal, you give it a special name, right? It's like calling an arbitrary triangle a non-isosceles triangle. But that's how it is. So this is what is meant by isospin-violating dark matter. So it's a dark matter that couples differently to the proton and to the neutron. Now, you may think that this is a very exotic kind of dark matter. So perhaps that's why it's not so relevant, and we can limit ourselves to the case in which these couplings are actually the same. But this is not the case. We can obtain these isospin-violating scenarios actually in many different models. Here are 3 examples. Dark photomediation. So you assume that the dark matter interacts with the standard model particles via a dark photon. So the dark matter is a fermion, and there is a dark photon that mediates the interaction with the dark matter particles. Because of this mediation, the coupling to the neutron is 0, because the neutron doesn't have any electric charge. Okay? And therefore, these couplings are not the same. This ratio is actually 0. So there is a coupling to the proton, but not a coupling to the neutron. Something similar happened with the interactions I mediated with the C, in the standard model C that we know. The coupling, we know that the C couples differently to the up and to the down quarks. Okay? And as a result, the coupling of the dark matter, which in this case would be kind of a fermion that interacts with this C, to the neutron and to the proton is also different. And in particular, you get this ratio, minus 12.5, between the coupling to the proton and the neutron. So it couples more strongly to the neutron than to the proton. Okay. And there is a significant difference, I mean, more than 1 order of magnitude. Another case that appears, for instance, in supersymmetry is when the interactions are mediated by light squarks. So if the interaction is mediated by an S quark, then this ratio is 0.7. If instead it's mediated by an SD quark, it's 1.5. Okay. The neutron and the proton have different U and D components, right? So it makes a difference whether the mediation is via a U squark or a D squark. So these are three examples in which we get isospin-violating dark matter. Okay? And you see that you can get 0, you can get a large number, you can even get a relative sign between these two couplings. Okay? And you can get something which is smaller than 1, something that is larger than 1. Okay? So it's not true that isospin-violating dark matter appears only in exotic models. Okay? These are simple models in which you naturally get isospin violation. Now, why is this relevant? Because the signals or the limits that have been obtained depend on this assumption. As I said, they actually assume that this ratio is 1. Sorry, what happened here? No. Yeah. Yes, so they actually assume that this ratio is 1. Okay? And this matters. So here is an example of why, what difference does this make. So in this figure, we have this ratio between the coupling to the neutron and the proton. Is varying over negative values, and here we have this factor Fc, and this Fc is the suppression in the sensitivity of a dark matter experiment. Okay. So what does that mean? That, for instance, if you know that Fn over Fp is minus 3.3, let's say, and then here you compute what the value of Fc is, then the limit that was obtained for an experiment, say for a xenon experiment, should be multiplied by this factor in order to get the real limit, because that limit was obtained assuming that Fn over Fp is equal 1. So if Fn over Fp has a different value, you have to multiply by this number that you get from this figure. And that's the real limit that applies for that value of Fn over Fp. Okay? So there is a different limit for each possible value of Fn over Fp, as expected. I mean, as I said, there are actually 3 parameters. And you see that this can make a huge difference. Okay? So this value here could be as large as 4 orders of magnitude. But what is more relevant is that these factors strongly depend on the target nucleus. Okay? So for instance, if you are here in this region, you see that Fc is much larger for xenon than for argon. Whereas if you are here, it's much larger for argon than for xenon. Okay? So this means that this rescaling that you have to make to the sensitivity is not the same for all different targets. It depends on what's the target you are using in your experiment. And the reason is so is because these different targets have different numbers of protons and neutrons. So this is expected. So of particular relevance, and this is relevant because here in this figure that I show, we are combining experiments which use different targets in it. So for instance, here, these LOX, Panda, and Xenon are xenon experiments. So the material that they use is xenon, whereas depth and dark side are argon experiments. Okay? So what we expect then is that depending on the ratio between Fn and Fp, the relative weight of these two different groups will change. Okay? And this can have a significant impact on the results. Okay? In particular, from this figure, it seems that this recent result, so this depth 3600 line is a limit obtained this year, and this is an argon experiment, as I said. It seems to be completely relevant. Okay? So remember that the way we interpret these figures is the region above the lines is excluded. Okay? So Xenon experiments have already excluded all the regions above these lines. And now this year there was this new experiment which excluded the region above the red line. But that region was already excluded apparently. So there is no new information there. That's what you get from this figure. Okay? And this is the figure that the experiment actually provided. But this is true only for Fn equal to Fp. Okay? If Fn and Fp are different, this is no longer the case. And as I said, the most significant effect is expected around this region. Because in this region, you see that Xenon experiments lose a lot of sensitivity, but Argon experiments don't lose as much. Okay? So this region is called, is around for Fn over Fp minus 0.7, and it's called xenon-phobic dark matter. So xenon-phobic doesn't mean that the dark matter doesn't couple to a xenon nucleus. Rather, it means that it couples significantly more weakly than expected. Okay, so this is where close to this peak here. So in that region, we expect that the previous figure will change significantly, because the Xenon experiments, which are in the case of isospin conserving more constraining, their sensitivity will be reduced by a factor of order 10 to the 4, whereas for Argon experiments, it will be reduced only by about 2 orders of magnitude. Okay? And this is what we get. So in the left side, I have the same figure as before. So these are the 3 Xenon experiments, and these are the 2 Argon experiments. Okay, and this is for Fn over Fp is equal 1. As I said, this is the same figure I just made it myself, but these are the same points. So now we are going to change the value of Fn over Fp. So here is 1, and here we take minus 0.69. So for clarity, I remove these 2 lines, which are always close to this dark red line. Okay? Because the relevant comparison is between the red line and the 2 blue lines. And this is what you get. This is the limit when Fn over Fp is minus 0.69. So you see, for instance, that the scale changes significantly. Here we have a limits that are of order 10 to the minus 6, 10 to the minus 4. Instead, here is 10 to the minus 9, 10 to the minus 8, okay? Because of this suppression factor that I said before. But more important than that is the fact that now this limit from depth, which looked irrelevant or is irrelevant in this case, actually becomes relevant. Because of this different value of Fn over Fp, this Argon experiment is actually more constraining than current Xenon experiments. Okay? So this experiment, which provided a limit, an apparently irrelevant limit, is actually constraining new regions of parameter space. It's just that when these regions are not do not exist for Fn over Fp equal 1. You have to go to different values, and in particular around this region, in order to get this result. So you see then that when you move from this isospin conserving dark matter case, the interpretation of the experimental limits changes significantly. Okay? So now we have that for this value, the leading experiment is not Xenon 1 ton, but rather this new Argon experiment depth. And we can also determine, for instance, what is the region where depth is more constraining. So there is certainly a region in this plane, dark matter Fn over Fp. So this region is not huge, so it goes for the values between minus 0.71 and minus 67. So all these points are close to the xenon-phobic region, because you need to suppress significantly the xenon bounds. Okay? And they don't depend on the mass at high masses, so this region in principle extends to arbitrary high masses in this plane. Okay? But so there is a region in this happens. Depth is actually more constrained. And this is a novelty, and this is an important novelty. So this other line here is the result from another argon experiment. It's called dark side 50. So it uses the same target as depth, argon, but you see that even in this case, it doesn't go beyond the Xenon one-ton limit. So it is only with the release of this new data this year with depth that argon experiment started constraining new regions of parameter space, not previously constrained by other Xenon experiments. So this signal what I call the end of the Xenon-dominated epoch, because over the past decade or so, Xenon experiments have actually been dominating these direct detection limits. Okay, we have different experiments. They are different parts of the world using Xenon, and they provide the strongest limits. But now we have that a new era has just begun, in which argon experiments are making an important contribution. And this new era will allow us, for instance, to test isospin conservation. Okay? Because now, if you are able to get, for instance, once you observe a signal, and you observe a signal in Xenon, and you observe also a signal in an argon experiment, you will be able to determine whether it is true or not that Fn over Fp is equal 1. Okay, you will have enough data to do it. This is something that you cannot do if you simply have Xenon experiments. Okay? You cannot discriminate the value of Fn over Fp. You need at least 2 different targets to do so. And this is one of the things that we will be able to do if this trend continues. I mean, if argon experiments continue to be toward the future competitive with Xenon experiment, at least in certain regions of parameter space. There is also an idea that one can use these different targets, for example, to probe whether the dark matter particle is Majorana or Dirac. In that case, you would need 3 different experiments, but okay, which is kind of an extension of this idea here. So this is something that you will be able to do also in the future. So this is my conclusion. So the idea is that isospin-violating dark matter is kind of a natural scenario. So there is nothing special about assuming that the coupling of the dark matter to the neutron and the proton is actually different. There's no reason to expect these couplings to be the same. As I said, from the experimental side, I mean, there are no indications that this is the same. And from the theory side, we have many models, even simple ones, in which these couplings are different and significantly different. But for historical reasons, direct detection limits continue to be presented only in this case in which Fn over Fp is equal to 1. Okay? And we are missing important information there. Okay? I illustrated this with the recent results of this experiment. Depth, which is an argon experiment, it just published some data at the beginning of this year. And this data is actually more constraining than current Xenon experiments for certain values of this parameter Fn over Fp, okay? Which is quite different from the conclusion you get if you simply observe the figure published by the collaboration. And then in the future, we will be able to test this assumption. So if we have different experiments using different targets, we will be able to measure or determine this ratio, Fn over Fp, once we have dark matter signals, and we will be able to say whether it is true that dark matter is isospin conserving or not. Thank you.
Questions?
Maybe in a question, for the coherent cross section for neutrinos, what is this ratio?
Yes, so this is the set mediated case. So minus 12.5.